Hey gang, this screencast is a follow-up to Activity 3, Benium, where we looked at how we determine the average atomic mass for a given element and its naturally occurring isotopes. So, to go off of where we already have started, when we look at matter in nature, we often find that there are different isotopes of the same naturally occurring element. For example, in the picture here we see different forms of what are going to be silicon atoms, so different isotopes. We've got ones that are purple, others that are green, and others that are red. Now, we can't fundamentally see the difference here. The model just color codes them to tell us that they're different. But fundamentally, isotopes of the same element differ only in their number of neutrons. So what that means is they'll have different mass numbers. So let's take a little bit more detail and dig into how we actually calculate average atomic mass. Now, we've added a little bit of additional information here, just kind of down at the bottom. I want to let you know that there are three isotopes that are shown in this model picture here for silicon. We have silicon-28, silicon-29, and silicon-30. The only key difference between those three isotopes is their numbers of neutrons. Now, when we have three isotopes, we can't just simply add up their masses, divide by 3 to find the average atomic mass. It's a little bit more complicated than that because we have to take into account how often those elements appear. And you can tell just visually from looking at this picture that the most dominant form of isotope of silicon is silicon-28. And if we go to the next slide and look at its actual abundance, we'll see that it dominates handily. So here's that graphical view of the distribution of the three isotopes of silicon. Here you can clearly see again that the dominant form is silicon-28 and much smaller percentages of silicon-30 and silicon-29. So from that we can actually do a little bit of predicting. If we were to kind of draw a simple number line that had our number values of our possible isotopes, 28, 29, and 30, and these are all in AMUs respectively. If we had to kind of pinpoint where the average mass would be, we wouldn't say 29 because there's hardly any 29s and hardly any 30s. In fact, what we would probably say is our mass is probably going to lie just a little bit above 28. And this can be helpful because the most dominant form of the isotope is going to be the one that most heavily influences the average atomic mass. I mean, what we're really doing here is taking something called a weighted average. Now let me show you how to do this mathematically so you can check your prediction and make sure that your actual calculated value validates what you thought it should be. Okay, so here's our solution and how we deal with the mathematics of calculating an average atomic mass. So our equation must take into account the abundance and the mass of each of the naturally occurring isotopes. So since we have three isotopes and three abundances, we're going to have three parts to our solution. So the average atomic mass will just be the decimal form of 92.223%, 0.92223, times the mass of that particular isotope, which is 28 AMUs. We add that to the contribution from the next most abundant isotope, which is silicon-29, 0.04685, times its mass, 29, and then we're going to have to add to that one additional step. That final isotope of isotope silicon-30. Now, we do these individual products and then we sum them together and we get the average atomic mass, which is around 28.10 AMUs. Okay. Hope this was helpful. Have a great weekend. We'll talk to you on Monday.